So thank you everyone for joining us today. So we are the IEEE ComSoc TCCN Special Interest Group in AI and ML in security. So right now we are our chair is Professor Shubha. She's from Stevens Institute of Technology, and we are other all of us are four vice chair and. I am Debashi Roy. I'm from UT Arlington, and Dola Saha is from University at Albany. Hanif Rahabri is from RIT, and Moinul Hussain is from George Mason. So these are about us. I'll just briefly talk about the group. How many we have? 468 members in LinkedIn group, and it's actually growing. And please, all of you, please join our group following the link. You can also send us email if you want to get the link through the email. I mean, you can find us over in the internet through our using searching our universities as well. So what we do normally is earlier what we had done, this group is active for last many years, at least 3 4 years, and but I and two new member we got joined like this year. And so earlier they had done some of the activities like seminar activities of the distinguished professors and scientists. It started with Professor Vincent Poor, and then there were like it spanned over a year or so, more than that. Then we and those talks are also available in the internet, recorded talks and YouTube channel if you want to check out them. But after that, this year we started, as there are many new member and also like new faculties in the group, we started to do something like something new. So that's this series, Rising Star series. So this whole initiative is about to give a platform to the candidates or rising stars in this field to bring in their research and what they're thinking, or give them the platform to even practice their job, talk to a broader community. And maybe our goal is to foster more mentorship, employment opportunities, hopefully, and all that. So before this talk, I was talking to our speaker today. He's on the job market this year. So um, that's what this talk is about, to help the rising stars to showcase their work. So right now, the talk is 45 minutes, and it's meant in a job talk format, and there will be Q&A, and after that for 15 minutes. So earlier this is our third talk. We had two of them, one from GIE. She was from MIT, and then Nadia was from NIST. This is our third one. Normally in the talks, what we do, everyone is muted, and we encourage the audience to ask question anytime in the chat box, either any of us, either me or Moinul or everyone. You can ask your question, and at the end, we'll moderate those questions to the speaker. With that, so I'll just briefly discuss, briefly talk about our speaker today. So our speaker, Saidur, Mohammad Saidur Rahman, is a PhD candidate at RIT, Rochester Institute of Technology, in the Computing and Information Science Department. So he's also a security intern at Cisco Quantum Lab, Cisco Research, and his primary research focus in ML for security and privacy, and particularly in the problem spaces of malware analysis and network traffic. So with that, thank you everyone for joining. Thank you, Saidur, for coming here today, and we are very excited to hear from you, and the floor is all yours. Thank you. So I will stop sharing. Okay.
Can you see my slides? Thank you very much, Dr. Rai, for nice introduction, and thank you for to the IEEE Technical Committee on Cognitive Networks for inviting to this virtual symposium. So my name is Saidur Rahman. I'm a PhD candidate at RIT and a security research intern at Cisco Quantum Lab, as mentioned by Dr. Roy. Welcome to my talk, Machine Learning for Cyber Defense from Network Security and Endpoint Security Perspective. Looking into the recent statistics, we can see that the concern for cybersecurity from both security and privacy standpoints is greater than ever. For instance, Cybersecurity Ventures 2022 report predicts that the cost of cybercrime will surpass $10 trillion by 2025. This report also indicates that by 2031, only the ransomware damage could increase to $265 billion, which is a 13 times increase from 2021. Adding to these alarming security concerns, our privacy is also at risk, as the United States Congress has granted rights to internet service providers to sell our personal browsing history. Unfortunately, recent study also indicate that the current skilled cybersecurity workforce is insufficient to meet the growing demands of cybersecurity. For example, the International Information System Security Certification Consortium has recently reported that 4 million cybersecurity professionals are actually needed to address the current cybersecurity challenges. And even this staggering number may not be enough. While a collaborative effort from academic institutions, governments, and industries is necessary to prepare the skilled workforce needed to meet the demand, in the meantime, we can attempt to automate some of the workflows to address certain challenges using artificial intelligence-based systems. Considering this, there is an increasing discussion about leveraging AI to meet some of these demands in cybersecurity. Towards that end, my current research work broadly lies at the intersection of machine learning, security, and privacy that investigates AI-based intelligent systems to address security and privacy concerns. Specifically, I focus on two major areas of security: network security and endpoint security, with an emphasis on the problem spaces of malware analysis and network traffic analysis. In this slide, I show my research journey from the start of my graduate school back in 2016. In this slide, the x-axis is not actually scaled. So I started my research journey with two research areas: applied machine learning and network security in 2016 as a master's student. Then I built up on that, focusing on endpoint security problem spaces from 2020. From the mid of 2023, I started working on quantum network security. In all of these areas, I was fortunate to publish first author and co-author papers in top security and privacy journals and conferences. And as an incoming faculty, wherever I get the job, I plan to contribute working to investigate open questions in all of these three areas. So as you can see that my research covers relatively a broad spectrum in security and privacy. In this talk, I will first present two example research projects that represent the breadth of my current research interest. In the first project, which falls under the network security category, I will discuss our proposed state-of-the-art adversarial machine learning-based defense against website fingerprinting attacks, which is designed to protect users' privacy online through the Tor network. Afterwards, I will talk about the second project, which falls under the endpoint security category, in which I investigated the state-of-the-art continual learning techniques from the computer vision domain to develop an evolving malware classification systems. Additionally, in my ongoing research, I propose a novel continual learning technique tailored for malware classification, considering the unique challenges of malware data distributions. This is a relatively new research domain, and to the best of our knowledge, we are among the pioneers in this emerging research area. Furthermore, I will briefly outline my long-term and short-term research plan and plan for a grant proposal and teaching interest. So this project was published in IEEE Transaction on Information Forensics and Security in 2020, and a short version of this paper was published in ACM CCS 2018. As I mentioned briefly in the first slide, in a couple of slides, the concern for privacy is actually increasing and has become very much critical since United States Congress has given passed the legislation giving right to the internet service providers to sell our personal browsing history in 2017. And recent FTC report find that ISPs collects a lot of our personal data in which we have really very less options to restrict or limit the collection. So here in this schematic representation, we can actually get an idea how a potential attacker such as ISPs, autonomous systems, or even a local wireless traffic sniffers can exploit our network traffic and reduce our internet activity. We might think that a VPN might be able to address some of the concern of our privacy, but unfortunately, VPN is not actually enough to protect our privacy. And previous research also showed that VPN itself can be a malicious entity. So as a solution to the discussed challenges, Tor emerged as a privacy-preserving technology and is the most popular low-latency anonymous systems, with almost 8 million users each day and 8,500 relays around the world. Tor can protect users' privacy by routing the traffic within three nodes called the entry node, middle node, and exit node, which are in between a client and this actual final destination or the server. However, it turns out that Tor is actually vulnerable to traffic analysis attack. One such attack is called the website fingerprinting attack. A website fingerprinting attacker is considered as a passive local eavesdropper. Passive in this context means that the attacker does not have the capability to modify, insert, or delete any kind of packets. Rather, the attacker can just observe the network traffic flow. Local means that the attacker has the ability to monitor the network traffic between the client and the entry node. Several research show that a website fingerprinting attacker can de-anonymize the activity of a Tor client by just analyzing the network traffic, even though those packets are encrypted. Please note that in this case, we already know who is the victim or who is the Tor client. We are just interested to find out what he is doing over the internet using Tor network. So before going into a little bit in depth, let's try to see that how actually an website fingerprinting attack is performed. The attacker first needs to actually train a machine learning or deep learning classifier with the network traffic of the sites of his interest. To collect the network traffic, the attacker acts as a Tor client and then collect the network traffic, like in these examples of RIT and Facebook network traffic flow. And if he's training a traditional machine learning classifier like KNN or SVM, he needs to first extract different type of hand engineered features, then train the classifier. Or if the attacker is using a deep learning model, such as a convolutional neural network or long short-term memory, then he can just feed the raw traffic information for the training purpose. So after the preparation of the model is done or attack model is prepared, then the actual attack phase, which is the second phase of the website fingerprinting attack, in which the attacker is actually in the monitor mode. Like actual attack, the attacker oversee or observe the network traffic flow of a victim. He collects the network traffic and feed those network traffic into his trained machine learning or deep learning classifier. And the classifier is actually can predict or infer which sites a client has visited. So over the years, this attack has got a lot of attention to the research community. State-of-the-art website fingerprinting attacks are mostly deep learning based and have achieved over 98% accuracy to de-anonymize the activities of a client. So to defend this kind of attack, we need to find actually ways to confuse the trained machine learning or deep learning classifiers by concealing the identity, which in this case are called the network characteristics or traffic pattern. The pattern that the classifiers, machine learning or deep learning classifier are using or kind of using to infer the test network traffic flow. We can do so by two techniques, either by padding or delaying, or a combination of both, which is mostly preferable in the defense proposals. Padding enables adding some dummy packets, carefully inserted to distort the pattern of the network traffic flow. If we see these examples, if we assume that this is the original Google network traffic flow, and the attacker collects this network traffic flow, and if he feeds this traffic flow to his trained classifier, it is very much easier for the classifier to identify this is a Google network traffic flow. But if we paired some of the packet, as you can see as a dotted line, green dotted and red dotted line, then it will be a little bit difficult for the classifier to identify that this is a Google network traffic flow. Now, we can also delay some of the packets in between packets, which also distort the pattern of the network traffic. Taking the previous examples of Google, now if we can delay some of the packets, as you can see, there are some gaps in this original network traffic flow of Google. Now if we kind of rearrange or kind of add some of the delays in between the packets, or then it becomes a little bit harder for the classifier to actually distort, for the classifier to identify this is a Google network traffic flow. So these are the actually fundamental two strategies, and there is a kind of the ongoing research try to kind of tune either adding more packets or adding more delays, kind of or having a balance between the bandwidth overhead and the latency overhead. So considering the seriousness of this attack, we proposed a novel defense based on adversarial examples, which can fool a machine learning model with high confidence. Hence, before going further, let's briefly look at the vulnerability of a machine learning model, because essentially the website fingerprinting attackers are actually using the advanced machine learning and deep learning model to craft these kind of attacks. Now, if as a defender, if we can find some ways to make those models do some mistakes or make the models produce a lot of error, then would be successful as a defender. So the idea of the adversarial examples is that small changes in the test sample can fool a trained machine learning classifier to misclassify the sample. As you can see from these images, it is hard actually for the human eye to distinguish these two images of cat, but the machine thinks that they're actually different, which means small amount of noise which is added to the original test sample is now classified as a guacamole with even higher confidence. Now, combining these two properties, two properties, which is a small perturbation or small changes, and fooling the trained classifier actually incorporate the objective of a website fingerprinting defense. And these small changes will provide us lower bandwidth overhead, which is one of the objectives of website fingerprinting defense, and also it will fool the classifier, which means our defense will be successful. We can protect privacy against the website fingerprinting attacker. Now, in this slide, we actually introduced the Mockingbird design in a very high level. First, for the Mockingbird to work, we need to actually make the network traffic flow of two sites indistinguishable. Like, just briefly, I would like to talk a little bit more on this. Like, as you can see, these two cats looks exactly like similar, but the learning model actually thinks they're different. That's what our purpose is as well for the website fingerprinting defense. That, for example, if you are visiting a particular site, for example, Google, the collected network traffic that should show that to the machine learning model that this is actually not a Google network traffic flow, rather a different the traffic flow of a different websites. So from that context, as you can see, we have the original network traffic flow, which is the source network traffic flow, which website, particularly the website that we are going to visit, and we have a target pool, which means the targets which for which kind of our original network traffic flow will be made kind of similar to. Now, we'll send those target pool and original network traffic flow traffic to a perturbation vector, which will change the network traffic flow pattern, and then generate a perturbation vector. We'll add this perturbation vector to the original network traffic flow and send those to a detector. This detector actually recursively will tell us whether our perturbed version of the network traffic flow, we call it adversarial trace, actually can fool a website fingerprinting attack model. This goes through multiple times and it changes, the traffic is changed multiple times. And finally, once we see that our perturbed network traffic flows actually fools the detector, then we evaluate the final evaluation based on adversarial training, which means we train the model or train the attack model with all of the generated adversarial examples or adversarial traces and test the attack performance. So in the lower level, actually, there's a kind of high level representation. In the lower level, you can see how actually that's done. So assuming that we would like to actually visit a website from RI team, and we would need to pick another target trace, which is not RI team, which is any of the sites, this Facebook, Instagram, CIA, it can be any number of target pool. So we pick one of the instances from the target pool, in this case, Instagram. Now the purpose would be to make the RIT network traffic flow look like the Instagram network traffic flow. So first, we have measured the L2 distance between RIT sample and the target sample Instagram. Then we try to minimize the distance between these two samples. After that, we compute the perturbation vector of a trace by computing the gradient with respect to the each burst. Burst in this context actually means that the network traffic flow of a particular direction, either incoming packets or outgoing packets. So as I mentioned, we continue this process n number of times, and of course, then we could do this for any number of times. However, in our research, we see that this also actually introduced a lot of computational cost, added bandwidth, attack, also it's dependent on the attack accuracy. So in our experiments, we see that n equal to 500 provided us the best performance. So for Mockingbird to work, we have to maintain some specific constraint as well, which is suitable for website fingerprinting defense purposes. The computed perturbation vector sigma should be always positive, and we have to force that constraint every time we do this kind of perturb or generate this perturb network. Because we would like to restrict the packet drops, because packet drops will cause retransmission and the end user experience will be hard. And this is particularly problematic for Tor network because Tor is inherently is a little bit slower than the general network in general browsing activity. So right now, if we are kind of trying to, as I mentioned, that make the RIT page look like Instagram, if you look closely, we can see that the RIT has two packets in the first burst of RIT traffic flow. Like this is just showing green and red as the outgoing packets, incoming packets. So as I mentioned, burst is called the sequence of packets in a particular direction. Now we change this network traffic flow burst by burst. So as you can see, RIT has two packets in its first burst and Instagram has one packet. And if we want to make it look like Instagram, we would have to drop one packet, which we cannot do. In addition, the perturbation needs to be at least a certain minimum, because otherwise the perturb traffic will not actually fool the classifier, which is why we add a constraint to change the target if the perturbation is less than a constraint. Like the iteration number, we can provide any small value as the threshold. In our experiment, 0.001 actually provided us better performance. Now, if these conditions is not met, like both of these conditions, then we need to change either both of the conditions or any of the conditions is not met. We need to change the target sample from Instagram to any of the other randomly picked target, which in this case CIN, and continue this whole process again. Finally, we get our new trace called RIT prime by adding the perturbation vector sigma to the original network traffic flow of RIT. So our evaluation shows that our defense costs less bandwidth overhead, and it is better than the two lightweight state-of-the-art defenses, WTF pad and walkie-talkie. At the time of our work, walkie-talkie was not broken, but later with our work, we showed that walkie-talkie is also broken and WTF pad was also broken by another attack. And in addition, we can see that our defense does not have additional latency. Our defense provides us improved security, reducing deep fingerprinting and worse CNN attack accuracy from 97-98% to 42% and 35% respectively. Deep fingerprinting and worse CNN are the state-of-the-art website fingerprinting attacks. In addition, we can see that the top two attack accuracy is 57% for our defense, whereas the top two accuracy for walkie-talkie is 97% and 92% for walkie-talkie and WTP respectively. Why this is important? Because if the top two attack accuracy is higher, which means the attacker has some advantage to scope down the possible number of kind of the website that the victim is visiting. So if he's a persistent attacker, it would be possible for him to actually increase the precision in his attack model. So to recap the first project, we can see that website fingerprinting is a threat to user privacy, even though the traffic payloads are encrypted. And our novel defense Mockingbird provides improved security and improved performance, while existing lightweight defenses are undermined by deep learning-based attacks. So now I'm moving to the second project, which is a continual learning for an ever-evolving and dynamic malware classification systems. For this project, we will present the result of our first published paper and the results from our ongoing research effort. One of the prominent reasons for the rapid growth of cybercrime is the growth of malware to exploit different endpoint systems. Among other reasons, nowadays, it is relatively easier to develop malicious code and put that to the internet to spread out to the different network systems. Looking into the latest statistic from AV Test Institute, we can see that the number of malwares and potentially unwanted applications have grown from 200 million in 2013 to 1.2 billion in 2023, which is a growth of 600%. Looking into the malware growth statistic in a micro level, we can see that AV Test Institute detects around 500,000 of new malware and potentially unwanted applications each day. In addition, VirusTotal, which is another popular crowdsourced engine, registers 1.8 million unique pieces of software each day. This huge volume of new malware and software releases causes antivirus vendors incremental cost and training times. To handle this kind of challenges, antivirus vendors have three less than ideal options. First, they can expend tremendous training effort to frequently retrain the model over all the data, which does not necessarily solve the problem. Second, they can remove some older samples while retraining with new data, which provides attackers an edge to reuse older malware instead of writing new ones. In addition, the model will eventually forget those removed samples, in the later phase of the learning. Finally, they can train less frequently at the cost of not adjusting to the distribution, which enable a novel malware to evade the system relatively easily. As you can see in this figure, this is a picture taken outside of my apartment in Rochester. It's kind of the same tree in different seasons, like winter, summer, and fall. So essentially, in malware space, actually, we observe that similar malwares, but it's kind of written differently, in different kind of attackers or different malware writers, and actually has the similar properties. And we need to kind of incorporate those kind of distributional changes to our model as frequently as possible. So to address this type of mentioned challenges, continual learning can be a viable alternative. Continual learning is a branch of machine learning which acknowledges the continuous distributional shift in the data. Essentially, a continual learning-based model learns non-stationary data which are observed periodically or in a different time period. The data distribution of each of these periods is different. In continual learning literature, data from each time period is often referred to as the task, and these tasks can be new classes or new samples of the existing classes or even new objectives of the model. We can see a schematic representation of a continual learning training and inference in this figure. As the start of the continual learning training, the model learns data from time period 1, and the inference objective is to identify whether a test sample belongs to that distribution or not. In the next iteration of learning, the model learns data from time period 2, and the inference objective is to identify whether a test sample belongs to data distribution 1 or data distribution 2, and the process continues. Continual learning is fundamentally inspired by human learning process. And as a human, we learn by observing new things. And the learned knowledge is somehow stored in the hippocampus of our brain in the forms of abstract representation. In the continual learning literature, the continual learner model is compared to as the frontal cortex of our brain, which observes new data. And the storage of the data is considered as the hippocampus. The two major benefits of continual learning is the relaxation of the need to store all the data, which eventually reduces the storage cost. It can reduce computational cost as well by relaxing the requirement to retrain over all the data. However, unlike human brain, continual learning model is prone to catastrophic forgetting, which causes the model to forget the learned data. In a security application like malware classification, forgetting has serious implication, and it would essentially reintroduce some of the vulnerabilities in the systems. Continual learning research effort is primarily centered around overcoming catastrophic forgetting in a continual learning systems. Depending on the type of data distribution shift, continual learning can be formalized into three scenarios: domain incremental learning, class incremental learning, or task incremental learning. In a domain incremental learning scenarios, the number of classes in the learning process remains fixed, but the distribution of the model of each of the classes changes in terms of covariate shift. In a class incremental learning, on the other hand, the class distribution changes in terms of the emergence of new classes or new families of malware. In a task incremental learning settings, the objectives of the model changes for each of the tasks. For the interest of time, we'll only discuss domain incremental learning and class incremental learning for this talk, as these scenarios are the most relevant ones. A typical malware classification pipeline actually follows first identifying whether a test sample is a malware or a goodware, which is essentially a binary classification problem. Then in the lower level of the analysis, we try to find out the family of the identified malware, which is a multi-class classification problem. A family is a set of malware programs that have significant overlap in their code, such that they are considered by experts to be a group within with common functionality. The last layer of the pipeline is to identify the broader category or the behavior of the malware, such as whether the particular identified malware is an adware or ransomware or a banking trojan or kind of backdoor, which is also a multi-class classification problem. Now, if we combine this continual learning scenarios and malware classification pipeline, we proposed a formalization of continual learning scenarios for malware classification, where domain incremental learning considers the distributional shift with the emergence of new malware, class incremental learning considers the emergence of new malware family, and task incremental learning considers the emergence of new malware category. Considering the challenges of malware domain mentioned before, continual learning can be a viable alternative to address these challenges by offering to relax the storage requirement and computational cost for retraining. Towards that end, we investigate the state-of-the-art continual learning techniques, which are designed to solve problems in computer vision domain. Because none of the previous work explored continual learning for malware classification, and we endeavored to explore the research gap between these two problem spaces. We explored 11 different continual learning methods from 3 broad proposed continual learning category: regularization, replay, and replay with exemplars. For the interest of time, we leave the details of this of each of these category. So we compared in this published paper the performance of the studied techniques with 2 benchmarks, none and joint. None is basically where there is no continual learning techniques applied to mitigate catastrophic forgetting. And joint is where training is performed over all the training data till the current episode of learning. Looking into this result of EMBER dataset, which is a popular malware research benchmark dataset, in the domain incremental learning experiments, we can see that none of the continual learning techniques are actually effective to reduce catastrophic forgetting. It might seem that, whereas gradient episodic memory and experience replay are the only 2 less performant techniques, but if we look a little bit carefully, we can see that the line of non-benchmark is actually somewhere here, and it seems that other techniques are actually performing closer to none, which is we'd like to go towards this green line. And for the class incremental learning setting, we can see that all of the continual learning techniques also actually suffer to provide a better performance than non-benchmark, except iCurl. iCurl is a replay-based with exemplars-based techniques, which replace raw data of the previously observed classes based on a memory budget, which means it needs to have a strict memory budget. We'd also like to point out that the more and more classes are being introduced in the model in the learning episode, you can see that the iCurl performance is going down. So it started with 50 classes, and we increment 5 classes in each of the learning episode. And at the end of 100 classes, the performance actually went down. Still, it's the winner among all the other 11 techniques. So, well, the results seem to be a little bit unexpected, and we are surprised to see the limitations of existing computer vision-based continual learning techniques to mitigate catastrophic forgetting in malware domain. These results have motivated us to perform an extensive exploratory analysis to understand the difference between standard dataset studied in continual learning domains, such as MNIST, and standard malware datasets such as EMBER. We explored the data and feature complexity in these 2 datasets and also the effect of real data distributional shift. So our investigation starts from analyzing the MNIST 2-class t-SNE projection. We can see that the 2 classes of MNIST is nicely separable. And if we look into the 10 classes of MNIST, even though there are some data points which are kind of here and there, but still as a human eye, we can actually point out that there are 10 clusters. However, if we analyze the EMBER in the similar setting, we can see that the EMBER 2 class, which is a binary classification, is harder than MNIST 2 class problems. And for EMBER 10 class, we can see a it's very hard for human eye to actually distinguish whether there are 10 clusters or not. But this is the projections of Ember 10 classes. And so basically for Ember, it appears that the dataset complexity is significantly higher than image space, and feature space is much more semantically rich. We also analyze the effect of real data distribution shift. Once we say the real data distribution shift in this context, because in continual learning, most of the research are done by artificially producing a distributional shift with the MNIST dataset, which is called the permuted MNIST protocol. Fundamentally, the original feature space is permuted using a particular permutation value, randomly selected permutation value for each of the learning episode. And Ember data has 12 months data representing 12 tasks. And we also have taken permuted MNIST data for 12 tasks. And visually, we can see that cluster for MNIST, even though these are 12 tasks and a lot of randomly permuted values are there, but still they form clusters. Those are kind of different clusters, still they form clusters. But if we take the Ember data, which does not necessarily form any type of clusters, and these are very big mess, and fundamentally this proves us that this problem space is relatively different and also complicated than the MNIST problem space. So from those analyses, we wanted to go a little bit deeper into the analysis. We find out that the frequency of malware and good error sample in each task month. And if you look into the last column in this table, you can see that the value of this column is actually represent the number of families from which the number of malwares came from. So a little bit looking into the closer look for the January data, there are around 32,000 malware samples, and these 32,000 malware samples came from 913 families. And if we consider the malware data distribution for each of the task month is forming a cluster, assuming that they form a cluster, each of the family actually forms a smaller cluster in this big cluster. And this also indicates that malware data are heterogeneous in nature. So we have some different exploratory analysis, but for the interest of time, let's summarize our exploratory analysis. We see that malware data distribution in each of the tasks contains multiple sub-distributions with on an average of 800 families. And a lot of new families emerge and old families observed infrequently. Substantial number of samples without AV class labels are noticed in the Ember dataset, and the priorities of the families in the distribution changes over time because the prominent families which were identified in the earlier phase of the learning do not remain prominent in the later part of the year. Taking into all of these properties and challenges of malware data distributions, we propose a novel continual learning technique for malware domain. Previous work emphasized that the need to replay both representative and discriminative samples for an effective replay-based continual learning technique. In addition, we also observed that malware data distributions are heterogeneous in nature. Towards that end, we propose a novel replay technique that can maintain diversity among the replay samples. The reason we took a replay technique is because in our first paper, we observed that the only replay-based technique, iCard, actually worked relatively well compared to the other techniques. And as such, we propose to maintain 3 properties for our diversity-aware continual learning technique, which first one is a family-based sample selection to accommodate varying families. Then we consider selecting samples which are closer to the cluster mean to pick the most representative samples. And we also consider picking samples or selecting samples which are farther away from the cluster mean. Combining these properties, we propose 2 variants of our novel replay techniques. For each of the variants, we perform experiments with another 2 subvariants. As we have mentioned that our proposed techniques is a replay-based continual learning techniques. Hence, let's briefly discuss how replay actually works in this context. In this schematic representation, one indicates the initial phase of the model where we initialize the model by training with available data, and then we store the initial data to the storage. After the initial phase, the model becomes a continual learning model or enters into the continual learning phase, where it observes new data, and some of the stored data using a replay buffer. The key question of the replay-based continual learning techniques is to investigate different ways to fill out this replay buffer with a given budget constraint. Hence, we proposed two variants of diversity error replay. First one is based on isolation forest. Isolation forest is one of the widely used anomaly detection techniques and robust technique for outlier detection. Unlike other anomaly detection technique, isolation forest starts by separating anomalies from the beginning and continues till each of the samples are separated from each other. In a high level, we attempt to explain the process of isolation forest-based sampling in this slide. Assuming that after task one, we have data stored in each family in a storage. When new data comes in, we first send those, stored data to the isolation forest module with a memory buffer constraint. Then we get the replay samples at task two. Or, for the task two, we get the replay samples, it's kind of a little bit smaller storage cluster. Then we combine this new data and the selected samples from the given by isolation forest, which becomes the test data for training, and then we train the model. Note that in this process, we ensured that fundamentally this isolation forest picks both samples from groups of the representative samples and samples from the groups of the anomaly samples or discriminative samples. The second variant of our proposed technique is based on learned weights of the previous learning episode. Some previous work on replay utilized compressed replay, where extracted weights from a trained model is used in various ways to be replayed with the current data. For our work, we do not replay the weights. Rather, we use the weights of the model to identify the anomalous and similar weights, and then we backtrack those anomalous and similar weights to the sample repository using a mapping function. We explain the process in a schematic representation. Assuming that we have our trained model from January with different family data like juicy, ferret, or emotet. When we are in February, showing an example of family ferret, we have January ferret data, we have February ferret data. We combine these two data and we run through the model to get the weights of the model, which is this model, which is trained from the month of January, which means the previous test. Then we send those weights to the isolation forest module to get the anomalous weights and the anomalous weights and the non-anomalous similar weights. Then we send those to our mapping function to backtrack to the original feature space, and finally we get the training data for this particular test. With this data, it's done kind of iteratively to get all of the training data from this mapping function, and after that we train the model for this February test. So we have extended our evaluation to a large scale, a data set, including Ember, and also we have collected another large scale data set from Andrew Zoot repositories to to test the generalizability of our model, both on Windows malware data set and Android malware data set. In this slide, we show the summary of our results. We'll be omitting some of the details, but in summary, we can see that our techniques, IPS-R and AWS-R, which is the ratio variance of our techniques, actually outperform the previous prior work like experienced replay, AGM, and generative replay. And it is on par or a little bit better compared to a global reservoir sampling, which is also one of our proposed techniques. And we can see that for actual domain incremental learning settings, ratio variants perform better than the uniform variants. And we see the similar trend with Andrew Zoot dataset, where our techniques outperform the prior art significantly and either perform better or on par with the GRS techniques, which are global reservoir sampling. In addition, we'd like to point out that our techniques, you can see that it's actually providing us closer to the joint level performance, which means where there is no, it's done with all of the accumulated data at once. And I'd like to point out that the total number of samples for Andrew Zoot was around 650,000, which means we could get this similar level of performance with significantly lower number of samples. Now, in this slide, we're looking into the results of class incremental learning for Ember. We can see that for class incremental, the results is even better. For all of the cases, actually, our technique is not only better than the prior art, but also better than this GRS random sampling technique or global reservoir sampling techniques. And our analysis show that actually for class incremental learning, uniform variants perform better than the ratio variants, where we saw that for domain incremental learning, ratio variants performed better than the uniform variants. We observed the similar trend of the results for Andrew dataset. We only compare the iCarl performance for Andrew because for the with the Ember dataset, we observed that other techniques didn't really perform well, and iCarl was the kind of compared between these four, iCarl was the better one. So we only took iCarl to compare for the Andrew data set. And we also observed the similar trend that our techniques with, you can see that with 20K samples, our techniques are performing significantly better than other techniques, including GRS and iCarl. So to recap, on the second project, in this research, we attempt to bridge continual learning and malware classification for an ever-evolving malware classification systems. And our results show that computer vision-based techniques come short to address catastrophic forgetting phenomena for malware classification. Hence, we proposed a novel diversity-aware replay techniques for malware classification, which incur state-of-the-art results in several configurations. Specifically, our techniques show visible improvements in class incremental learning scenarios for both Windows and Android malware dataset. And we also see that for domain incremental learning, ratio variants outperform the uniform variants, and for class incremental learning, uniform variants outperform the ratio variants. We are actually drafting the paper for the submission. We did submit the abstract. We are right now submitting the full paper in a conference. So we are almost at the end phase of the talk. For the future research, I plan to continue my current research focus on continual learning for malware analysis and machine learning for traffic analysis, with some more problem spaces, including optimal gradient space investigation for malware classification systems, investigating generative AI techniques for generative replay-based techniques. In addition, I plan to resume my research on a large language model for malware analysis, which I started back in 2020. In the machine learning for traffic analysis space, I plan to broaden my research to video fingerprinting, in which we have some preliminary work. And now I plan to investigate deeply into this problem space. The last but not the least, I'm interested in looking into the fingerprintability of voice over IP network traffic. Finally, I plan to expand the breadth of my research with quantum network security, which is an emerging research area. At present, as a security research intern at Cisco Quantum Lab, I'm investigating quantum key distribution in enhanced solutions for anonymous communication data center and to provide quantum resistant data security. We have recently submitted a paper, and we're working to submit a patent. We got approval from Cisco. We're just working to submit to the officially to the US Patent Office. So after joining as a faculty, I plan to submit several grant proposals based on my current and planned future work on the space of malware analysis, network traffic analysis, and machine learning. I have identified some of the viable programs in NSF, DoD, DARPA, and Air Force Office of Scientific Research. In addition, I plan to apply to some industry grant from Google, Cisco, and OpenAI. And the last but not the least, a brief about my teaching experience. I taught a graduate level seminar course on advanced malware forensics in spring 2023 with students from diverse backgrounds, including minority groups and individuals of deaf and hard of hearing. I'm broadly interested to teach any of the undergrad or graduate courses in computer science. However, I'm mostly interested to teach courses which are within my research focus. In addition, I would like to study a special topic course on quantum network security. Throughout my academic journey, I have had the good fortune of collaborating with various academic institutions and industry partners. I would like to express my gratitude to my advisor and to RIT, as well as to my collaborators from these institutions and industries. I'm also grateful to the NSF for their generous funding, which has enabled me to pursue my research. Thank you very much for staying through this presentation. I would be happy to answer any questions.
Thank you, Saidur. So I think it was great. It was really a job talk, and I think it was very well organized and well paced. So thank you for that. So we have one question here so far. Q&A. It came around like it came around like 20 minutes after you started your talk. So it was like, how many websites did you considered? I am not sure which slide it was.
I think it's about the first
Okay,
project.
okay.
So for the website number of websites for Mockingbird, it was 83 websites in a closed world setting.
Okay, yeah. So number of sites, right? And then there is another question. How did you get the data? Are they real world or synthesized? And how you compared results?
Oh, thank you very much for the question. So for the data, we actually collect the data in your lab. For the network traffic data, we have the data crawler, and those data are also publicly available to download from the GitHub repository, which is given in which we provide the Google Drive URL to download the data. We do not necessarily publish the raw pickup files because those are huge in size. Rather, it's a pre-processed version that can be used in a machine learning model. And for the Ember data set, those are also real world data. Ember is a a real world malware data, and the extracted features are publicly available for Android malware data set, which are also real world Android malware and Android goodware, which can be collected from Android Zoo repository. We collected those data, we extracted the features using driven features code, and then but we publish usually the pre-processed version of the data in our GitHub repository. Comparing the benchmark for the website fingerprinting attacks and defense, fundamentally, we have the prior art. So we compare our performance with the prior art. For malware data set, essentially Ember has a benchmark. So we compare with that benchmark, which is widely adopted both in academic research and also industry research.
Thank you. So for the data you collect in your lab, do you like publish them, or how big are they normally?
Yes, all of our data are published, but we publish the pickup files.
Okay, pickle
But
files.
because pickup are very large, so we only publish the pre-processed version of the data.
Pre-processed, okay, I see. Mhm.
I don't see any more questions. Let's wait. But I have, okay, I see there's another question. There are billions of websites, and considering only around hundreds websites, how you justified your work? I'm asking because I'm in the state of justification of my own work. This is somehow related with your one.
That's a great question. Thank you very much. This is a very common one in website fingerprinting or traffic analysis. So the results that we are seeing is a closed world accuracy. Closed world accuracy, fundamentally, yes. There are billions of websites. So there is another evolution called open world evolution. So we didn't show the results in this slide. We have those results in the in our paper. But fundamentally, if our systems for the defense, attacks a little bit different. For the defense, if we think that our defense work in a closed world settings, which within 100 websites, if our defense is successful in the world, and attackers in this closed world cannot be successful, if you can make the project that into scale in the open world, the attackers will never be, or it will be very much difficult for the attacker to be successful in the open world. So for the defense, closed world performance is mostly accepted because if the attacker is not successful in this kind of smaller settings, he will not be successful in the larger settings. That's the difference for the attack. Now, for the attacks, now question is that whether this closed world attack performance is enough. That's why actually in the attack phase, there's a work on the open world precision. We try to tune the open world performance, and there's for example, there's 100 websites with this closed world, then maybe 500,000 of or 1 million of open world websites to evaluate the effectiveness of the attack model. I hope that answers your question.
Yeah. I think there's one more question. In terms of comparison, did you simulate previous papers with your data set?
So fortunately, actually these OWT paired, we broke this this was from our lab as well. So we already had those data and already had those, and the authors were also co-authors. So we didn't have to simulate. We ran those again. We had the data, we had the code, so it was easier, relatively easier for us to rerun for our papers. And also because we collected those data set by ourselves, so we didn't have to do any kind of simulation. We could just use those raw, real data for our evaluations.
Okay. So I have a question actually. So about the features that was used for fingerprinting, website fingerprinting, like you mentioned about the burst, the direction of data, uplink and the downlink. What other kind of data you have used for training?
So direction, so in website fingerprinting cases for Tor, specifically we look into the packet directionality and packet timings for an end-to-end model. The reason I'm showing this slide is because earlier version of the website fingerprinting attack used, extracted some of the hand-engineered features. It came out in 2017 paper and 2016, 2014 paper. So then from 2018, we had the end-to-end model. Basically, you just feed these incoming and outgoing packets. So essentially, you look into this is kind of maybe outgoing packets, incoming packets, outgoing packets, incoming packets. So essentially, we just feed these in some sort of representation. We represent this as +1 and -1. It can be any other representation, but prior work used +1, -1. So you can feed this directional information, and you can get a very good very high accuracy in your attack model. You actually beat all of the hand-engineered features-based attack model. In addition, in another of our work actually, which we show for the comparison, no, we don't show that here. So another work which uses the TikTok, which was published in PEDS. In this work, we used, on top of the directionality, we also used the packet timings. So these are the only two sets of information that we can actually necessarily use for Tor network traffic flow, because the packet sizes are kind of the same, because cell size is 512 bytes for Tor packets. Tor. So those are, the previous work showed that those are not useful. The other packet is and data, because those are encrypted, so we cannot use the payload. So the side channel information that are available to us is the packet directions and packet times. And with packet directions, previous work got a very high accuracy, and also we combine packet direction with packet timing, which is a very noisy information. And in this work, actually, we show that even using packet timing, we can get even better performance.
Yeah, that's great. So I have one last question is about the defense. So to generate those adversarial examples, like do we need any kind of what are the assumptions about the attacker? Like for example, if the attacker changes its classifier model, or if it changes its model, is it going to affect the performance?
Oh, that's a very good question, actually. Which means if I understand correctly, you're saying that if the attacker uses an advanced model, maybe right now we are using CNN. For this work, we used a CNN. Maybe the attacker is using an LLM, a very powerful model. Then
It could be anything else. Yes.
Exactly. So we actually show our evaluation in our paper as well, with the kind of that whether our attack actually also work with futuristic advanced attacks. So fundamentally, because adversarial examples has a property called transferable property or transferability property. So which means that the adversarial trace or the adversarial examples that we have generated for a particular model, that will remain as adversarial examples for another advanced model. We also show additional evaluations for that okay, we generate adversarial examples with, for example, a weaker model. There's another weaker model called AWF, automated website fingerprinting, from prior work. And we use that smaller kind of weaker model, and we test the attack performance of those generated traces using an advanced models such as CNN. And we show with our evaluation that still our our defense remain immune to those kind of advanced attacks. So you're right to assume that the attacker will be smarter and he will improve the attack model even better. But with this kind of approach, even though the attacker will be smarter, your defense will remain intact.
Okay. That's interesting. So is there any possibility of something like an arms race? Like whether the attacker can retrain itself with these perturbed samples over time.
Right. That's also another important point. So if the attacker, I think if the attacker can generate all possible adversarial traits and retrain the model with the adversarial training mechanism, can the attack be successful? Which would be very much hard and resource intensive. And the attacker needs to be very motivated, because for a closed world, even for a closed world scenario of 83 websites, there are for each of the websites, I think I forgot the exact number, there are, I think, around 500 instances or 500 samples for each of the class. So which means the attacker needs to generate, all of the possible kind of permutation permitted sample, and which will be enormous. And if you increase the number of closed world classes, the attack accuracy will be even lower. So attacker needs to be really that kind of motivated or nation state attacker to generate all of the possible cases.
Yeah. Okay. Yeah, sounds good. Thank you. Interesting research.
Thank you very much.
I don't see any more questions. So this is recorded. So it will be uploaded to our YouTube channel. So you can also access, the viewers can access the slides from there. I'm seeing some request for slides. So the video will be there. So I guess it'll be okay. I don't see any more questions coming in. Devashri, do you have any question?
I think we are good, and we are also running over time, so maybe you can conclude.
Yes. Yeah. Okay. All right. So thank you, Saidur, for the very interesting talk. We look forward to see you again sometime somewhere else, maybe. Okay. So again, this is recorded and it will be uploaded to the YouTube. It will take some time, a few days, to upload it to our YouTube channel. All right. With that, goodbye, everyone. Goodbye,
Thank you very
Saidur.
much.
Thank you. Bye.